About format string vulnerability. This is an interesting one. Let me move into the right directory for this. All right. See what I've got. All right, clear. All right, so we've got, you get this vulnerability, you get your data. Now here I'm going to have Metasploit installed. I think I've already got it installed on this machine. I do. All right, good. So I'm going to, I'll quit it when it gets done starting. I've already downloaded the program, which is good because, as I mentioned, wget is not usable anymore. You have to download things through a browser. All right, so this program will run, and if you run it on hello, it'll just print hello. So it takes in data and repeats it back. And here is the C code that does this. So here, it takes a command line argument with **v here. So you have the name of the program and then some data. Here's the data coming in, and it's going to copy that data into a buffer, which has room for 1,024 characters. So by the way, there is a buffer overflow if you were to feed in more than 1,024 characters, but we're not going to exploit that. We're going to exploit the other vulnerability, which is here. It prints the buffer without specifying the format string. I don't know why C allows you to do this, and I could say that about all these flaws. C is a very dangerous language. You really shouldn't print anything without specifying the format string. But if you want to, you can do it, and it will choose some default format. The problem is, when you enter the print method, it will look on the stack for a format string, and if it finds something like it there, it will fall for it. So if I put a format string in here as the data, when it looks on the stack, it'll look at the first argument, which came from me, and it looks like a format string, so it will then look for the second argument, which was not specified by the developer, and it will print some leftover data sitting in memory with the format string. So let me get out of here. Yes. All right, so clear. All right, so if I run this program and I give it AAA, it prints it. But if I give it a format string, like %x, it prints some weird data because now it interpreted the data that came from me as the format string, and it just looked beyond that for the next word in RAM and showed it to me. So this is an information disclosure vulnerability. I'm able to see the contents of memory which the developer did not intend for me to see. And I can put in more of these, %x, %x, %x. I can get 4 bytes, and now, since that's a format string, I could put a spacer in there like a dot, and separate them like this so I can see them. So here's some data coming out. Now notice, if I do this, if I put AAA here, then this should look familiar. 41 is A. So in this case, the data I put here is on the stack, and I'm seeing it here. So I can control data at this point by putting it there. That's one thing. But however, what's really insane about this, so as it is, this would only be an information disclosure vulnerability, and you could perhaps find a way to reach something important, like a password or some configuration thing you want. But what's really deadly is, for some ridiculous reason, the developers of C included the %n format. And what the %n format does is write to RAM. It takes the address you fed in and it writes to that location in memory. I have no idea what this is good for, except for hackers to take over your box, because that's insane. And so now it crashes with a segmentation fault because it turns out that these are invalid locations on the memory. But since I can control it here, I can feed in a memory location, and then I can write to that memory location. So I now have not only a read, I have a write operation under my control. And you can totally take over the box with a write operation. So how do you take over the box with a write operation? Well, if you take a look at if I go into GDB, actually I could use objdump too. I'll follow the project though. If I go into GDB, D204, and then I disassemble main. All right. So you can see the system calls here, the C function calls. I call print here, okay, and then if I go to the next page, I call string copy, and then print, and then put character, and then exit. So those are the C system calls. Now the way the way you call a C library function is you don't jump directly to it, you jump to an offset table. There are two offset tables because think what might happen. You might recompile your program so the addresses from that side change, or you might update your operating system so the addresses from that side change. So both of them use an indirection table so that even if you change them, the old program will still work. So these things are called relocation records, and you can see them. They're called procedure linkage table and global offset table, and you can see them with objdump. So if I quit from here and do objdump -R on this program, you'll see here's the actual addresses it uses for the library calls that it uses. It only uses a few libraries: printf, string, copy, exit, and putchar. And here's the actual address. It jumps to this location when it exits. I can write to that location and make the call to exit go somewhere else. And this is what rootkits do, by the way. They change the addresses of system routines so all the programs on the box now do unexpected things. It's like changing the operating system underneath your programs. And that's what we're going to do here. So if I can write to that memory location, then when the program tries to exit, it will go to the location I chose instead. That's how you take over the box. So I can write to that location. I can do it in the debugger. Let's go back in the debugger. And now I can examine the current value of that location here. I'll just examine one 32-bit word at the location of the exit pointer. And it tells me that's pointing to exit. And here's the address. That's the correct address. 0804 and this junk is the right address to get there. Now I can run this program that I've loaded with this data. And here it is. The thing you should be used to this is that address backwards, 0804A014. That's that address backwards. And we saw before that whatever 4 bytes you put here will end up as the 4th word on the stack. So %x, %x, %x will just print out 3 words, and %n will write to that address. That's using the format string vulnerability to change the contents of memory at that address. And so now it will crash, and if I go look, I've changed that address, so instead of pointing to exit, which should be 0804, it now points to 1B, just all zeros and 1B. So that shows that it works. I can change that address, and it causes the program to crash because it tries to execute code at that address. Now I just need to choose a better value to put in there. And so we have to talk about what value is put there. What value is put there is a total of all the bytes that have been printed so far. So I guess the original purpose of this was for some kind of formatting of output. So that's why I printed this small number of 1B. That's how many total bytes have been written so far. So what you do, if you want to write a whole 32-bit word, is you do 4 write operations. So I do cat f1.py. Let's see, thought I had it. Oh, I haven't got it. I'm going to have to add it here. Okay, so let's add it in nano. f1.py. All right, so here's the code. All right, and let me get rid of the stupid colors. I'll nano it with -w none. Crap. -y none maybe? There, okay, always forget. All right, so here what I do is I write to the location 0414, then I write to 15, 16, and 17. So moving incrementally 1 byte each time I write, and so I'm going to write each of these. I can just put them here. These strings are going to do it. This is the 4 bytes that move there. Then I need to move forward 4 bytes. That's what's going to happen. So, and here's the format string that goes at the end, %x, 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 %n, %x, %x, %10n, and so on. So this is the pattern that writes to those 4 bytes. So if I do that, then I'm going to, chmod, make it executable. And then go back into GDB. Okay, and now I can run taking data from that program, which you do this way, f1.py. That'll run that program and feed it in as a command line argument to this program. And now it crashes, and you can see here the value, and that's the value where it crashes is the value I wrote, but you can also verify it by explicitly looking at that memory address. It's 37, 30F, 47, 40F. This is the total number of bytes written so far, and after each one, it increments by 8 because I write 8 more bytes. So now I've written a sort of uncontrolled 32-bit value to there. Now what I have to do is control it, and therefore all you have to do is you have to pad it. So what you do is you add, you can repeat something many times in the format string by putting a number here. So I'm going to put in 256 extra letters plus some more to change the last byte to be something under my control, and I'm going to do that times 2 times 3 times 4. So each one of these is going to wrap around some number of times and then write the value there. And I have to keep incrementing it because I can't decrease the total number of bytes written so far. So first I write 256 bytes, which would go all the way around to 100 and hex, give you 0, and then I add enough further to get there. And this number 29, you have to change to match whatever this layout of the stack is on your system. So this might be off. But what I'm trying to do is I'm trying to get this address, AABBCCDD. If it's working, I'll get that address. Otherwise, I'll have to adjust that 29 number. And I find it best to just do it by trial and error. If you're real smart, you might be able to figure it out. But it's easier to just try until you get the right number than to be smart. So there's F2 that's going to do those 4 write operations. And I chmod to make everybody able to run that program. And then I go into debugger. And I run, taking the data from f2.py. All right, and it runs. And notice I didn't quite make it. I wanted AABBCCDD, but I'm off by quite a bit. So I was hoping to get the desired value, but it looks like on my system it's off by quite a bit. So let's see. Instead of AA, I got B1. So that's A, B, C, D, E, F, 0, 1. I'm off by 7. Okay, so I need to change that number by 7. And I think I need to make it larger by 7. Let's take a look. It's a, oh, I got to get rid of stupid colors. And I got a minus sign there. All right. Yeah, it's a negative number. I think I need to change this to 22. Let's try that. See what that does. All right. Run. $f2.py. Nope, now it's worse. Okay, so I needed to go the other way. Like I say, I just do it by brute force rather than trying to get too smart. So let's go in here. It was 29, so I need to add 7 to it. And this is hex, so I think that would make it 30. See what that does. Yep, now I get AABBCCDD. Okay, so I had to make that correction, and it will depend on your system, exactly what that number is. All right, now I'm almost done, because all I have to do is, now I can control that address. So now I put in dummy shellcode, and we've done, we did this before in the buffer overflow exploit. So now I have that address, and I'm going to put in shellcode here. I'm going to inject into memory, after all this stuff, which does the writing to the return pointer for the exit function, not the return pointer, but the pointer to the system call for the exit function. I'm just going to add a NOP sled and shellcode, 100 bytes of NOP and 250 bytes of break, because that shows room. That is a place where I can put a real exploit. And so you run this one. This is f3.py. And I put in this stuff, and then remember I have to change, I have to get rid of the stupid colors. I wish there was a way to make it stay forgetting the colors, but I haven't found any way to make it remember this. Okay, and now this number has to be 30, not 29. Figured that out before. All right, so now if I run the debugger, and I run taking data from f3.py, all right, now it exited normally, so what I'm going to want to do, oh, I forgot, the program didn't run. I forgot to make it executable. All right, that's one thing that's wrong with it. And I think that's the only thing wrong with it. Let's try it again. Run the debugger, run $f3.py. Yes. All right, so now it crashes with AABBCC, which is what I expect. Here's all the junk it printed. Here's the dummy shellcode. And so now I can look in memory and find it. So I can do, first I can look at the address of the exit pointer. And that includes, that's what I expected, AABBCCDD, so I'm in control of that. Now I want to figure out what to put in there instead of this fake value. And you do that by looking on the stack. X100 bytes on the stack. This shows me the stack. So here's random data. Here's the NOP sled, all the 90s. Here's the dummy shellcode, all the Cs. So all I have to do is jump anywhere in this region. I'll hit the NOPs, and that'll go nop, 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 and run the exploit. So any one of these addresses would do. I just need to pick an address in the middle of the shellcode and go there. That's the trick. And like I say, the address will be different on your system. Be something like that. So now you just run F4. Let's get out of here. I'm going to copy F3 to F4 and then nano F4. And I'm going to get rid of the stinking worthless colors that are always in my way. All right. Whoever put colors in a Unix terminal should just knock it off. I never want them. Anyway, all right, and so the address here that I want to put is that address instead. There. And so it's, I think they're in forward order. Maybe they're right to left. It is right to left. What, 14, 15, 16, 17? I'm not quite sure what order to put them in. Let me see if I can tell from my example here. FF, okay, it's B4 is the high byte. Okay. So I want to put FFFF here. This is where I put the address. FFCF6C. There. There. So now it should write that address and hit the NOP sled. And I don't think I have to change anything else here.
You have 5C.
I have, oh, no, 6C and 6C, that's fine. What's wrong?
Oh, on your B1?
On my what?
Your B...
Yeah, B1 is, oh, I have 5C instead of 6. Oh, thanks for telling me. By the way, that would probably work, but we might as well have 6C. That's why you have 100 bytes of NOP sled. You can afford to have very mistakes, and it'll still work. So this might work. Let's run the debugger. And run $F. Oh, I don't have, it's going to be executable because I copied it from executable. Okay. And now it hit the break. That's what you want. Because that means if I do the X100X ESP, it hit the NOPs and ran through the NOPs and then hit the first break, which was here, and stopped. And that is at address FF, bunch of Fs, CF9C A0 A4. So it should have stopped at A4, and it's A5, the next byte. So you know it worked because it ran through the NOPs and hit the break. So now I can execute that. And now all I have to do is insert real exploit code there. And for that, we can use Metasploit to write the code. There is a test for bad characters. I don't think I'll go through that. And then you can generate your real shell code here. It turns out several characters are bad, just the ones you would guess. Characters that would terminate an input variable in a command line are a null byte, a tab, a carriage return, a line feed, and a space. So you have to avoid all those characters. And that's what this command will do. It'll make a shell bind, which will start listening on a port and execute commands. And it will avoid using those characters. So this will create malware, and the final size of the malware is only 133 bytes. and we made enough room. We had 100 bytes of NOP sled and 250 bytes of CC, so there is enough room. So you just have to add that to your file instead of the dummy shell code, and you then get a you can then get a listening shell. So you can then connect on this port that's listening and remote control the machine. This is a very simple attack. Anyway, that's what I wanted to show you. It's good, clean fun. And all right, so I got some tips there in case you get in trouble. Anyway, just make sure you're using an Intel processor, and this should be all right. And the interesting thing here is that when you have a write operation, you can still take over the box by writing to an area that'll be used for an address later. And these system calls are one good place to do it. There's quite a few good places where you can take over the write exploit. All right, so let me stop this one.